Hi there! Welcome to the 19th episode of the Synth project, where we are going to build a synth together. In the last episode of the series we introduced the design of the LFO, the low frequency oscillator. Today we will work on that design and build the whole LFO module. We will tune it and we will test it in the synth rack. Many things to show, and so without any further ado, let's jump into the video. Enjoy! Here is the package with the PCBs I ordered, based on my design from last episode. I got 5 of them, and I'm going to use 2 since the module that I'm going to build will contain not 1, but 2 LFOs. Assembling always requires the same technique. First we attach all the mechanical components. I started with the IC sockets, followed by the power supply socket. Initially I decided to assemble one section at a time to be able to test it independently from the other sections, and so after the power supply socket I started reconnecting the passive components for the first section, the triangular and rectangular generator. First the capacitors and the resistors, and last the transistor. But after I did that, I changed my mind and decided to build the whole circuit and tune and test everything at the end. So I continued to add all the other components, and at the end I added the ICs to their sockets. After that I had yet another change of mind. I usually solder directly all the cables to the board, and then I solder the other end to the hardware on the back of the panel. This time, however, I decided to use connectors on the PCB side. The reason for the choice is essentially the simplicity for testing. If I had soldered wires all over the board, it would have been dangerous to have all those wires around while tuning and testing the circuit, because of all the possible short circuit that could have happened. Using sockets allows me to attach connectors only in those places where I need them at any given time, and thus avoiding any trouble. And so here is the PCB, completed with all the electronic components and the hardware. Time to check the circuit and see if it works correctly. Right now I have connected the power supply here, and then the potentiometer to control the frequency. I didn't connect the potentiometer for the depth, because I'm not going to test it right now. If this potentiometer works, the other one will work as well, because of the way the circuit is built. And I also connected the oscilloscope probe to the triangular wave output. Now the circuit is powered up through this power supply, and here is the output for the triangular wave, and you can see it's very nice. Let me try to change the frequency a little bit so you can see where we can go. So this is the maximum, about 25 Hz. Rotating the potentiometer the other way, and the frequency slows down. Keep going down. We should be able to go below 1 Hz. Let's see if that's all true. Let me change here the setup of the oscilloscope so we can trace better what's going on. Going down some more. And as you can see now we are this is 800 milliseconds per division, so we're doing 1, 2, 3, 4, 5, about 6 division. So the period is now 4 point something over 4 seconds for a single period of the triangular wave. And so with this will allow us to do a lot of interesting things with the synth. And we will see that later when we test the complete module. So let's now move the oscilloscope to the next wave, which is here the square wave. It should be fine too. And here it is. Right now it's slow moving. Let me accelerate it a little bit so we can quickly see if everything is fine. There it is, a very nice square wave. And now let's move to the next one, which is supposed to be the sine wave. This has 2 trimmers that need to be adjusted, this one and this one, so we will have to see what we have right now. And Right now the wave, of course, is not correct, so I'm gonna move the first to input now, the R19, and let's see what we can get with that. Okay, look at that. I can change it at will, but just by changing the point where the two transistors of the differential amplifier are working. The other input, the R27, should be the one that basically adjusts the symmetry of the wave. And okay, so I guess we have to go the other way around a little bit. This seems symmetric enough to me, and let's adjust a little bit more the sine wave. Yeah, I guess this is okay. We should be fine with this. So now we move to the next one, which is the ramp. And the ramp is right here. Move this. Okay, and connect it here. This should be the ramp. And there we go. And you can see there is a little glitch over here, which is due to the fact that the first part of the ramp and the other part of the ramp are not exactly aligned. And to align them, we have to use the input R35, which I'm moving now. As you can see, this way I make it worst, and this other way I go to the opposite directions. So we have to find the exact point where the two lines of the ramp are perfectly aligned. Okay, let me change here the scale of the oscilloscope so you can better see the ramp. Okay, it seems fine at this point. Okay, so this is our ramp. It's pretty good. Let me see changing. Yeah, look at that. There is still a little difference over there. Let me see if I can adjust it a little more with the potentiometer. This is worst. Okay. This seems pretty good now. So let's increase the frequency. Let's see if it stays that way. Yeah, it's pretty good shape. Okay, now let's see the last one, which is the sawtooth. So let's move it over here. And there it is, which is exactly the opposite as the ramp. Once I finished assembling the two LFOs, it came into my mind that we don't have anything available to figure out what's the current frequency of the LFO once it is installed in the Synth rack. The thing is that with the VCO we can easily hear the actual frequency and how it changes, but with the LFO, since the frequency is subsonic, we have no way to understand if the LFO is set the way we want. Since we cannot hear the LFO, I thought that we could probably see it, and we can do that if we use an LED piloted by the output of the LFO itself. The LED will blink more or less slowly and will give us an idea of the current frequency of the LFO. Here is the circuit that I decided to use. It is very simple, and it is built around one single transistor. The LED will be powered through the collector of the transistor when there is a signal to the base. I put a 10K resistor on the base to limit the current in the base emitter junction. Such current will be amplified by the transistor and will be presented at a much higher value on the collector where I put the LED. However, I also added a resistor on the emitter of the transistor. The resistor will limit the current through the transistor itself and therefore through the LED, keeping it at a value that will not burn either component. I also decided to use a triangular wave as the input for this circuit. This way, besides the blinking of the LED, I will also be able to see an increase and decrease of luminosity in the LED, and this will help understand whether the circuit is working or not when the selected period of the oscillation is very slow. If I had thought about this earlier, I could have added this functionality to the PCB. Unfortunately, being this an afterthought, I will need to assemble yet another board for it. And since I don't want to make another PCB for this very simple circuit, I will use a single perf board and I will put on it the circuits for both the LFOs. Here is this new circuit that I built on a perf board. And basically there are two of them actually. This connector is for the power supply. These are the two inputs for the signal that comes from the two LFOs, in particular the triangular wave. And these are the two LEDs that are supposed to tell us how fast the LFO is oscillating. Here are the two transistors, the resistors on each side, so each of these sides reflects exactly the circuit that we examined on the schematic. And here is the test circuit for this device. First of all, we have only a power supply of plus 12 volts and ground, which is inserted over here on the appropriate socket. And then right now I'm making work the circuit on the right side, and you can see the LED is oscillating, and it's oscillating right now at 25 Hz, because in order to test it and know exactly how much is the frequency, I decided to use for the test the output of my function generator, which is currently set to 25 Hz. And with a triangular wave, so it's exactly the same wave that is going to be used for the LFOs in the synth. I'm going to now decrease the frequency and see how the LED behaves in these conditions. So let's take a look at the LED. There it is. You can see that it's still blinking very fast, and now we are at 20 Hz. I'm going to go down to 15 Hz now, and you see the blinking now slowed down a little bit, but it's still very fast. Let's slow it down more. Now we are at 10 Hz, and you can see clearly now the blinking. There it is. And if I go even down, now I'm at 5 Hz, and you can see the LED going on and off at that frequency. Let's go down to 1 Hz. See, you can still see the LED working. And now if I go even further down, I can go to 0.9 Hz and 0.8. So you see I can still have a view of what's going on without the need of any instrument once I have this LED on the panel of the LFO. Right now I am 0.7 Hz. Going to 0.5 now, and it's still working just fine. And go further to 0.1. Let's see how it behaves in that case. So this is 0.1 Hz, and basically there is one pulse every 10 seconds now, and you can see the LED working accordingly. And because this LED is controlled by a triangular wave, it is not exactly a switch between on and off, but the LED goes on progressively, a little bit at a time, and the same when it goes down. You see, it illuminates a little bit at a time, and goes on, see, and then it goes off the same way, a little bit at a time, slowly, until it turns off entirely. We can do the same test on the other side, to make sure that the other circuit works too. So I'm moving the signal to the other side. There we go. And the other LED behaves exactly the same way. Here it is. Let me increase a little bit the frequency so we can see better. We can see quicker what is going on. Okay, so this is 1 Hertz. Okay, everything works fine. So I guess it's time now to move on to the next step of this project. And here is the CAD design of the module case, built with the OpenSCAD. The front panel clearly shows the two sets of holes for the hardware components of the two LFOs, one on the top and one on the bottom. At the center of each of the two sections you can see the small holes that will be used for the LEDs. On the side panel instead you can see the two sets of holes to attach the two PCBs and a third set of holes to attach the perf board for the LED circuit. This one instead is the set of decals for the front panel. Each LFO has two potentiometers, one for the frequency and the other one for the depth of the control voltage. And there are also 6 jack sockets for each LFO. One socket is for the control voltage input, and the other 5 are for the 5 different output waves. Incidentally, the reason for me to use 5 different outputs rather than a single output jack with a rotary switch to select the shape is to have more versatility. Having all the outputs available at the same time allows us to use more than one shape at the same time if needed, as long as we use the same frequency. And also having 2 LFOs allows us to simultaneously use 2 different frequencies for each of the output signals. And here is the printed version of the case for the LFO. You can see here the 2 sections for the 2 LFOs, so we have 2 of them in the same case. And these are all the holes. There are 6 holes for the jack connectors and 2 for the 2 potentiometers. And this is the hole for the extra LED that I decided to add to the design to show with its blinking the rate at which the LFO is working. These are the decals for the LFO, and so these are the 2 sections, the upper section, the lower section. We have the potentiometer for the frequency, the one for the depth control for the control voltage. These are the 5 outputs: triangular, square, sine, ramp and sawtooth. And the same is for the one on the bottom. So this basically will hold right over here, and we will have 2 nice LFOs in the same container. What I have to do now is just to connect the 2 wings to the case, and then we'll proceed with painting it over here, attaching the decals, and then painting again with a transparent paint to hold in place the decals. These holes over here are a new design that I made for the wings. I found in the previous cases that I designed that when I glue the wings in place they tend to move. So to avoid that from happening, I put these 2 holes with these cylinders that go inside over here, see, like that. So they hold in the exact place the wing while the glue dries up and sets. Here, see, like that. And basically it holds in place the wing without the possibility of it moving. So I will now proceed with gluing the 2 wings, and then I will put the first layer of paint, white paint, and then we will put the decals, and finally the final layer of transparent paint. And here are the wings just glued, as you can see. So we just need to wait for the wings to dry, and then we can paint. And here is the case with the wings already glued together. Now it's time to spray the paint on the front of the case. After spraying a few layers of white paint on the front panel of the module, it was time to attach the decals to it. I proceeded by cutting the sheet into 2 segments, one for the upper half and one for the lower. I didn't feel comfortable to use one single huge piece of decal. This way is more manageable, at least for me. After cutting and rounding the edges of the two sections, I immersed it in water one section at a time and transferred the decals on the front panel. Then it was just a matter of making sure there were no air bubbles under the film and that the surface was dry. I completed first the upper section and then I did the lower section. Then I waited some time to let the decals dry, and they glue, of course. After applying a few layers of transparent paint on the front panel to prevent the decals from detaching over time, I waited for the paint to dry and then I cut the film covering the holes with a sharp knife. A few brush strokes and then the front panel was done and clean. Before adding the hardware component and the boards to the module, I glued some copper tape on the back of the front panel and on the inside of the side panel. The copper tape helps with shielding the PCBs from possible noise and also puts all the metal body of the hardware on the front panel at the same ground potential, helping increasing even further the EM shielding. After putting the copper tape, I had of course to clear up all the holes on the side panel and the back of the front panel from the copper tape itself. At this point I mounted all the components on the panel. I started with the potentiometers of the upper section and then the jack sockets. Then I moved to the lower section, and again the potentiometers first and then the jack sockets. And finally all the components were mounted on the panel. How does it look like? Next step was to prepare all the cables to connect the PCBs to the components on the panel. I used wires of different colors to easily identify them, and I crimped on one end of them the pins for the connectors. Then I inserted the pins in the appropriate slots of the connectors. When you do that, make sure to follow the schematic to figure out the order of the pins for the connectors. If you invert the order, the LFOs will not work correctly, and if you connect the power connectors in the wrong way, you can even risk of burning the components on the PCBs. So be careful to match the order of pins on the schematic and on the PCB. Note that the schematic numbers all the pins to easily identify them, and the PCB instead marks the pins number 1 with a square pad instead of a rounded one, and that should make it easier to correctly identify the position of all the wires. Once all the cables were ready with one end attached to the proper connector, I soldered the other end directly to the component of the panel. That way all the cables were attached directly to the components on the panel and had the other end ready with a connector to be inserted in the right place on the PCB. To attach each PCB to the side panel, I used 8 screws and 4 spacers. Same with the perf board with the LED circuits, which, however, had to use thinner screws because of the size of the pre-drilled holes in the perf board. I started by connecting the spacers to each of the boards. Then I connected the boards to the side panel one at a time. When you do that, attach each screw without tightening it. Once they are all attached, then tighten up everything. The holes are perfectly aligned, but it is always better to use some caution to avoid complications. Once all the boards were attached to the side panel, I plugged the connectors for the LED circuits and then I inserted the LEDs in the holes in the panel, forcing them a little bit to make sure they would hold in place. Then I used some glue to prevent them from moving in the future. And then, finally, I waited for the glue to set. Once the glue was set, I plugged in all the connectors to the PCB, making sure to match both the boards and the front panel elements with the sockets on the PCBs. Once all the cables were connected, I used a few zip ties to reduce the clutter behind the front panel. Finally, I attached the knobs to the potentiometers. In this project I am using knobs of different colors for the various functions. Continuing with the same rules used for the VCO, I used the blue knobs for the two depth controls, and I used yellow knobs for the frequency controls. And the modular assembly was then completed. Finally, the long-awaited moment of installing the new module in the Synth rack. Okay, let's start by connecting the new module to the power supply of the Synth, and then we will check if it works, and if it does, we will fix it in place. So first of all, we have to attach all the power cables. There's one over here, and then one over here. And this power cable, I have only, although the connector is always the same with 4 pins, there are only 3 cables attached to it, because really I'm not going to use all 4 of them, because the 5 volts is not used in this case. And for the LED we even have only 2 wires, because it only uses a plus 12 volts. So this goes over here. Now I'm going to attach these wires to the closest power supply connectors in the rail, and then we will try the component. So 1, 2, and 3. There we go. These are connected. Let's put this over here for now, and then we will attach it later on. So let's power it up. And you can see already that there's these LEDs that are blinking. Here, you can see them better now. And we can try to increase and decrease the frequency to see how this LEDs behaves. So this is going faster now, and on the other end this is going slower, slower and slower, and we can do the same over here, of course, for this other one. Let's see, each one on its own, and they blink depending on their own thing. And finally, it is time to make some noise. And after all that noise, after all those tests, it was finally time to screw the module to the rack. The synth is now ready for some prime time, now that we have a few modules already available. I still wanted to add several more modules, of course, of different kind, but I think the next step will now be to modify that old keyboard currently laying unused on the rack, and make it work to be able to play some real music. Let's start working on that in the next video. Don't forget to subscribe and to click on the notification bell to avoid missing the next episodes. I'll see you soon, and as usual, happy experiments!